Yeah, it's fine. I can talk to this one. Thank you, Tom, for the introduction. Yeah, I'm Gorka Irazoqui, and I will speak about a shared cache attack that works across cores and defies VM sandboxing. And we will see how can we apply it to AES. This is a work done with my two advisors, Professor Eisenbart and Professor Sunar, in WPI, in Worcester Polytechnic Institute, and more precisely in the Burnham Group Lab. Sorry, my bad. So this is the agenda that we'll follow. First, we'll talk about an introduction together with the necessary background to understand the attack. Then we will see how the novel side channel technique can reach the last level cache to extract information. Then we'll see how can we apply it to AES. We'll see the results, and we'll conclude the presentation afterwards. So let me start with an introduction of the cache side channel attacks history. So basically, they have been studied over the last 12 years, more or less. The first implementations were done by Tromer et al., for example, and Ajishmes. Tromer et al. Explored two sprite processes, which are prime and probe and edict plus time. And they showed it how to apply it to AES and recover AES keys. And then Ajishmes used the same prime and probe technique in the instruction cache to recover RSA keys. So these attacks are really nice, but they have a practicality issue because they are assuming that both victim and the spy process are being executed in the same OS, which indeed is not very practical. I mean, I cannot imagine a scenario where I can go to a victim's OS and execute the same process, well, a spy process concurrently with his vulnerable process. Also, they were targeting level 1 caches, and indeed, this translated to our model processors means that we have to execute the spy process and the attack in the same core, which again reduces the practicality of the implementations. So the question is if there is a practical scenario where cache side channel attacks can be applied. And yeah, thanks to the wide adoption of the cloud computing systems, we can see that cache side channel attacks found the perfect scenario where they can be applied. Why? Because in the cloud, two different users share the same physical hardware. This means that we can go to a scenario, from this scenario, for example, where we have two VMs that are executing processes in the same hardware, isolated by a VMM. This looks very nice, but it can turn to this scenario where one of them is a victim, the other one is a spy process, and the spy process is monitoring the hardware so that he can extract information from the victim. And indeed, this kind of attacks have been also studied. I guess our session chair can call the first paper. So the Hey You Get Off My Cloud paper, where they were able to collocate two virtual machines, or yeah, a virtual machine with a potential victim in Amazon EC2, and even figure out the traffic thanks to the cache monitorization. Then in 2012, Sang et al. Also were able to extract LGAML decryption keys from level 1 caches in virtualized environments, and in 2014, Jerome and Falkner, yeah, they were able also to use, well, they used the flash and reload side channel technique to recover RSA keys from collocated VMs. But this is important because this attack was applied in the last level cache. This means that we don't need to be collocated in the same core anymore, but this attack can be applied from different cores. And this is important. So, however, the flash and reload side channel technique has, well, it's based on the duplication features that are being executed in the hypervisor or the VMM. And indeed, these features might not be enabled in commercial clouds. So the next challenge is to find a new side channel technique that also applies to the level 3 cache, so that we can work across cores, and that doesn't rely in the duplication process. So basically, the duplication is turned off. So is this possible? We will see that in this presentation that this is indeed possible. But first of all, let me go for the background, and yeah, I'm kind of giving a hint of what we're gonna do, but yeah, let's ask ourselves why prime and probe has only been applied to upper level caches, to small caches. Well, indeed, prime and probe bases his attack, or the prime and probe spy process is based on the knowledge that the user acquires from the physical address. And indeed, with well, we know that users only see virtual addresses, and these virtual addresses have to be translated to physical addresses. Indeed, there is a portion of the virtual address that is not translated to, that doesn't suffer a translation step, which is the offset. The offset is directly depends on the memory page size. With regular page sizes of 4 kilobytes, this offset becomes 12 bits, which might not be enough to address big caches. We can we can go to a situation like the one we see in the slides, where let's say the set field is the one that tells you where your data is going to be located in the cache. And indeed, if the set field gets some portion of the physical page that a user doesn't know, a user doesn't know where his data is going to be located, and therefore he cannot apply the attack. But still, there are some advantages of going to a last level cache compared to the level 1 cache. First of all, we have more resolution. Last level cache accesses compared to memory accesses are much bigger, or are much more distinguishable than level 1 and level 2 accesses. And also, again, we can work across cores. This is important. We don't have to be collocated in the same core anymore. This is a much weaker assumption than before. The disadvantages of the last level cache is usually, in Intel processors at least, it's divided into slices. This means that instead of having a last level cache like the one we see in the slide, where we have 4 sets, for example, well, it's not going to be like this. This is going to be, for example, divided in 2 slices, a slice 1 and a slice 2. And yeah, instead of having 4 sets, each slice is going to get 2 sets. So basically, the user is going to be only able to to put his data into set 0 or set 1. And there is a, I shouldn't say unknown, I should say unpublic function, not documented by Intel, that decides between both slices, between where the data is going to be located. With these evidences, let's explain how the new side channel attack works. So basically, we want to make the offset bigger so that we can address the last level cache, so that we can control the last level cache. So how can we do this? Well, indeed, we can allocate huge memory pages, which yes, is enabled in most hypervisors from the guest VM. Huge memory pages, instead of 4 kilobytes are of a size of 2 megabytes. This means that the offset, instead of 12 bits, it becomes 21 bits. Well, this is much better. We can now control caches up to 2 to the 15 sets. And indeed, this is far from what we need, because most Intel processors have last level caches of 2 to the 11 sets at most. So basically, we are far from the limit. Now that we can control the last level cache, we can apply a prime and probe process. We're going to add a slightly different step here, which is the reprime process. But let me explain how this works. So basically, we first of all, as attackers, generate lines or memory blocks that fill a set in the level 3 cache. However, since level 3 caches are inclusive in Intel processors, we are going to experience something like this, where the upper level caches are going to also be filled. And since we want to clearly distinguish between last level caches and memory accesses, we don't want that evictions in the level 1 and level 2 caches affect our results in any way. So what we do is we reprime the upper level caches. So basically, we generate memory blocks that kick memory blocks in the level 1 and level 2 caches, but that don't touch the memory blocks in the last level cache. So now we have the perfect scenario where any eviction in the level 3 cache is going to give us the we're going to be able to distinguish between memory access and level 3 cache. Now, the victim comes, for example, and executes a process that might or might not use the set we are monitoring in the level 3 cache. Let's assume that he doesn't use the level 3 cache. So he will use a memory block that doesn't evict any of our red lines in the level 3 cache, and when we probe these 3 red memory blocks from the last level cache, well, indeed, since all of them still reside in the last level cache, we're going to see a low probe timing. However, it might happen the opposite, right? It might happen that the victim uses the set we are monitoring. And indeed, one of the memory blocks is not going to reside anymore in the last level cache, but it's going to reside in memory in this time. So basically, we're going to reload 2 memory blocks from the last level cache, 1 from memory, and this is going to give us a high probe time. The question is if this is still distinguishable. Well, indeed it is. We can see in the plot. the probability distribution of 12, the red distribution is, the red distribution are 12 lines reloaded from the last level cache, and the blue distribution are 11 lines from the last level cache and 1 from the memory. And indeed, this is the probability distribution over the hardware cycles. We can see that they are, not only the timing or the reload time is much lower when we reload all of them from the cache, but also the variance. The variance is an important observation that we make here because it's much lower as well. So basically, we can see that if we put a threshold between, let's say, around 300 cycles, we can clearly distinguish both cases. Again, this is true if we can control the slices we're monitoring separately. So how can we apply this to AES? Indeed, we're going to apply this to a T-table implementation of AES, and we're going to apply a last round attack, where the last round of AES looks somehow similar to what we are seeing in the slide. So we're going to try to monitor when a T-table position has not been used. There is indeed, let's say that we're monitoring table position number 1, right? So there's going to be only a ciphertext value that always uses that table position for this last round. Indeed, the one that holds this equation. So there's going to be only one ciphertext value that always uses that table position. The rest, they might have a chance or they might not have a chance of using it. So indeed, if we monitor when this has not been used, there's going to be only one ciphertext value that is going to show us the counter, a very low counter. And we can see it even, and once we obtain that ciphertext value, we can solve the equation byte by byte. We can see it in the picture indeed, where the x-axis plots the ciphertext value, and you can see the distribution in the y-axis normalized. So we see, well, indeed, a cache line holds more than one table position. So basically, we can't monitor only one table position, but we have to monitor many of them at the same time. But still, it's clearly, the distributions are clearly distinguishable, so we can still solve the equation and get the key that has been used. We can do this for all the bytes in the AES last round. So, however, there is a pre-step that we have to do before the attack. We have to know where the T-tables are located in the last level cache. But indeed, this is not a hard process, because so basically we can clearly distinguish, as we see in the figures, when a set has been used by the AES encryption and when a set has not been used by the AES encryption. Indeed, the right graph shows a set that hasn't used the set, since we see all the timings around 200 cycles. And in the left one, we can see a set that has been used by AES, and indeed a table position. Because we see low timings around like 8% of the times, and high timings around 90% of the times, which is actually the behavior we expect from a table position. So let me show the results. We implemented this in 2 different machines. One of them is an Intel i5-650. It has 2 cores, 2 slices. So basically here, the slice selection algorithm is easy to figure out. It's just using the 17th bit to decide whether it goes to one slice or the other. And we implemented this in Xen and VMware with Ubuntu 12.04 guest VMs. We also implemented it in a much more modern machine, Intel Xeon i5 2640v3 that has 8 cores, 8 slices. It uses many bits to select between all the slices that it has. However, we can still target the slices separately because we can actually figure out which memory blocks go to the same or collide in the same slice. We are using this with VMware, and we're using this time Ubuntu 14.04 as guest VMs. The results are shown in the picture, where the x-axis plots the number of encryptions we need times 1,000 to recover the key, and the y-axis shows the number of correctly guessed key bytes from 0 to 16, because we're using AES 128. And ignoring for a moment the green and the red lines, which do not plot the cross-VM scenario, let's focus on the other ones. We can see that the blue line, which is the Xen hypervisor in the Intel A5, it's the one that needs more traces to recover the key. And indeed, we think that it behaves worse than VMware because we're using a fully virtualized hypervisor here. This is adding more noise than a para-virtualized hypervisor. So basically, we believe this is the reason why we're seeing worse results in XM than VMware. We also observed that the Intel Xeon needs less traces also to recover the key. And we believe this is because the last level cache that the Xeon has, it's much bigger than the one that the Intel i5 has. So basically, a side process that is using the same set and it's creating false positives, it's much more likely that uses the same set in the Intel i5 than in the Intel Xeon. So yeah, but still in the worst case, even in the worst case, we can still recover the key pretty quickly. So the Xen case was, well, used. We were able to obtain the key in less than 3 minutes. So to conclude, so we showed that a new cross-core side channel attack that uses the last level cache is still possible, even when the duplication features are not turned on. So basically, we can still monitor the last level cache across cores. The only assumption we are using is that the guest VM or the attacker VM can use huge pages, can allocate huge pages to control the last level cache. We saw this, we demonstrate this in AES. We see that we can recover the AES key pretty fast. We have an additional stage, of course, the table location, but we saw that it doesn't add too much overhead. And the remaining question well, the question that remains is if tenants should be allowed to use huge size pages from guest VMs, or at least the way they do it now. That concludes my presentation. Thank you, and I'll take questions now. Thank you.
Go ahead.
Jethro Beekman, UC Berkeley. I was wondering, what is the workload in your test setup? Were there any other things running besides the measurement and spy processes?
No. There was nothing running at the same time, no. We believe, well, indeed we see in the results, right, that when you're using a fully virtualized, hypervisor that creates more additional noise and so on, we see that the results get worse, but no, apart from that, nothing else was running.
Have you confirmed if Amazon EC2 allows large page allocations?
If you can allocate huge pages in Amazon, yes, yeah. You can.
Okay. And have you tried running your attack on?
I would say not in this paper. Let's leave it there.
We'll take that offline. All right. Why don't we, unless there's any more questions, we'll thank the speaker again.